linear data structures. Things are linear, just sequential like this. Even hierarchical data structures, we may have to use a linked list approach. So what we saw so far is really the foundation, and now from now on we'll build on top of this. Okay. All right. So this is kind of a high-level example to really understand the difference between a single and double linked list, and also similarity between them. So single linked list, we should be familiar with this figure by now. So you have a head node. From the head node, we can go through one data node at a time, but you can only go through in one direction, starting from the head node further down. So if you have reached, say, the last data node, you cannot go back to the previous data node, because at the last data node you really don't store the address of the previous node. Or even in general, from one data node you cannot go to a previous data node. You can go only to the next data node, because you store the address of the next data node in the next node pointer field in the node. Okay, so that's a kind of a weakness of a single linked list approach. You cannot go back toward the head node. So if you want to be able to do that, you need to store the store the address of the previous node to the current data node, and that's what we are doing there with the double linked list. So in a double linked list, a node class will have three member variables. The data, it could be again anything like integer or a character or a string. You have to define it. Once you define it, we have to use that data type. Then you have the next node pointer, like the node class of a single linked list. You also have another pointer called the previous node pointer that will store the address of the node previous to the current to that node. Okay, so let us look at this figure here. So you also have, in addition to the head node that you used to have in a single linked list, what's called a tail node. So the head node will be used to traverse through the double linked list in what is called the forward direction. So from the head node we can visit this data node and this data node and so on. So that's called the forward direction. So this will be the first data node in the forward direction, and this is the last data node in the forward direction. Now using the tail node, you can traverse the list in the reverse direction. So in the head node, the only thing it needs to store is the address of the next data node, and the head node is a dummy node, so you don't store really the data, and there's no node really previous to head node, because first of all the head node is not a data node. So you store the previous node pointer some meaningful value only for the data nodes. For the head node, you don't really need to store the any value for the previous node pointer. So these two field values are not set up. So only the next node pointer value is set up to the head node, like we do for a single linked list. Now in the tail node case, you don't need to set up the data as well as the next node pointer, because there's no data for the node further down. So you need to store only the address of the last data node in the list in the forward direction, which will be this node at address 172 in this example, and that's the value for this previous node pointer for the tail node. So using that previous node pointer, now you can access this last data node in the list. Starting from the tail node, now we can access this data node. So now this data node will store the address of the previous data node, which is at address 152 in this example. So using from this data node, you can now access this data node, and from here you can go back to the previous data node, which is at address 132, and then that will store the address of the previous data node, which is 116. Excuse me. So now this is the last data node in the reverse direction, because we are now traversing the list in the reverse direction. So this is called the first data node in the reverse direction, and this is the last data node in the reverse direction. So there's no data node further down in the reverse direction or previous to it from the forward direction. So we set the previous node pointer to 0, because the head node is not a data node, so the previous node pointer is set to 0. And similarly here in this last data node, the next node pointer is set to 0 as we do for a single linked list case, because there's no data node further down. So we should not set this to be the address of the tail node. So this is the data node, that's the last data node in the forward direction. There's no data node further down. So this next node pointer should be set to 0. Similarly here the previous node pointer should be set to 0. So you should always remember that. Now in the single linked list case, we used a head pointer to store the address of the head node, and we do the same thing here. The head pointer stores the address of the head node. In addition, we need a tail pointer to store the address of the tail node. Okay, so those are the two pointers that will be the member variables of the double linked list class. So here I show a comparison between single and double linked list. So the node class in the single linked list will have these two member variables, the data and the next node pointer. Those are two member variables of the node class. So the next node pointer is of type node star because it's a pointer, it's going to store the address of a node. So that's why I say node star. So in the case of double linked list, this will be the node class, the three member variables declared private of the data, the next node pointer are similar to the single linked list. So I have kind of put things circled in a square, the things that are going to be in addition to double linked list. So in a double linked list, a node class, you are going to have a previous node pointer that also is going to store an address of a node. So it's a node star. Now in the list class for a single linked list, in the node class for the single linked list, you are going to have these member functions. So the constructor is a no argument constructor. Then the set next node pointer function will set the value for next node pointer. So we'll pass a node pointer, node star, and set next node pointer equal node pointer. And we have a get next node pointer function that returns the next node pointer value. So these are the member functions of the node class in a single linked list case. In a double linked list case, you're going to have the same member functions to do with the next node pointer, and you have to have similar member functions to deal with the previous node pointer. So you should be able to set the value for the previous node pointer for that node, as well as get the previous node pointer value for that node. Okay. So we use this function a lot, the get next node pointer, to move the current node pointer to the next node and so on. So similar to that, we can also use a previous node pointer to move the pointer address to the previous data node. Okay. So this figure also will be helpful for you to visualize things. So this is a node in a single linked list, and this is now your node in a double linked list. And the single linked list you can traverse through only in one direction, from the head node further down. In a double linked list you can traverse through in both directions. Okay. Now in a single linked list case, when you initialize the list, so this is how you initialize the list. So this is now the list class in the case of a single linked list. The only member variable you have in the list class in a single linked list is the head pointer that will store the address of the head node. So you declare that using node star head pointer. So the head pointer stores the address of the head node, and the constructor for the list, you are creating that head node and setting its next node pointer value to be null. Okay, so the head node's next node address is null. So that's like an empty list. So that is the kind of the the constructor for the list class in a single linked list case. And then you have a member function called get head pointer to return the address of the head pointer. So this is a member function in the list class for a single linked list. The double linked list, as I said, in addition to the head pointer, you need to store what is called a tail pointer as a member variable, and that will store the address of the tail node. And that's what we are doing here in the constructor for the list class for a double linked list. You see here, I don't explicitly call the list class a single linked list or a double linked list. I still call it as a list. So this is again the difference between ADT and data structure. So list is the ADT, and you are implementing that ADT as a single linked list. And here you are implementing the list ADT as a double linked list. So from a user point of view, he will still think this as a list, and he will create, say, like the list integer list we saw in the main function. Now the user doesn't need to worry about how that list ADT has been implemented. Okay, so that's why single linked list is a data structure, double linked list is a data structure, whereas a list is an ADT that can be implemented using any of these three data structures, as an array or a single linked list or a double linked list. So that's why I named the class as list itself, to indicate that's like an ADT. Okay. Now in the case of a double linked list based implementation, you have the head pointer and tail pointer. So when you create that list, you have to create the two corresponding nodes, the head node and the tail node. So this statement will create the head node, and head pointer will store the address of the head node, and this statement will create another node like here, and the tail pointer will store the address of that node. So in this example here, the head node is stored at address 100, so the head pointer stores that address 100. And let us say the tail node is created at address 196, and tail pointer is storing that address. So using the tail pointer, you can now access the tail node. So head pointer arrow set next node pointer is set to null, and the tail node's next node previous node pointer is set to null. Okay, so you don't need to touch the other pointers here. So for the tail node, you set up the previous node pointer to be null, and for the head node, the next node pointer set up to null. And this is how you create or initialize the list. You get an empty list basically. That's what you do in the constructor for the list class. So this is how an empty double linked list will look like. We saw earlier how an empty single linked list will look like. You just simply set the next node pointer for the head node to be null. So very similar to the previous thing. So this is how an empty single linked list will look like, right? So the next node pointer is set to null, and that's what we are doing also here for a double linked list. But we have to also set the previous node pointer to be null for the tail node. So this is how the empty double linked list will look like. So you can have the get head pointer function and get tail pointer function to return the addresses of the two nodes. Now I did not include a function, but you can add a function called isEmpty as a member function to the list class. And how you check whether that list double linked list is empty? You have two approaches, two ways to do that. One is check the next node pointer value for the head node. How you can do that? Head pointer arrow get head next node pointer. So if the head node's next node pointer is, so head node's next node pointer, you can get that value in the get next node pointer function. So if the head node's get next node pointer is 0, return it is true, the list is empty. You can also check that by doing what? Tail pointer arrow get previous node pointer. If tail node's previous node pointer value is null, then the list is double linked list is also empty. So in the case of double linked list, you have two ways you can check whether the list is empty or not. One of the two ways is good enough, because if head node's next node pointer is null, that means the list is empty in the forward direction. So the list should also be empty in the reverse directions. That means the tail node's previous node pointer should also be null. It cannot be the other way. Okay. Right. So with that, we finish this module. So now we'll use this as a basis to build up on top of the double linked list in the next two modules on stack and queue. But just to make sure there are any questions. Again, I think people are not reading the lines carefully in the description of the assignment. I don't want many screenshots, so let me pull out the assignment description. So I wanted you to take screenshots only of the extreme values. Alright, so case 2. So screenshot of case 1 with list size values of 1000 and 1000. So you see, in case 1 you will simply run for increments of 1000 and measure the time and everything for each of these list size values. For list size 1000, what's the run time? For 2000, what's the time? 3000, what's the time? And gather all the data, and we'll be plotting that data and all, or tabulating that data and all those stuff. But for screenshot, I don't want you to take the screenshot for each of these list size values. I want you to take only for the two extremes, the 1000 and 10,000. Similarly, for case 2, you take the screenshot for list size value of 1000 and a screenshot for the list size value for which you're getting the bad alloc error message. That means when you run for list size 2000, you may not get the bad alloc error message. So you don't need to take a screenshot for 2000 or 3000. You just take a screenshot for that list size value. It may be 7000, where at that time you get the bad alloc error message. Similarly, for case 3, you just take two screenshots, one for 1000 and one for 10,000. So basically, you'll have only 6 screenshots for the entire assignment. Is that clear now? And you can put together in the Word document. I hope everyone knows how to take screenshots and just put the screenshot. I don't want the entire computer screen, so you can use paintbrush to edit and cut just that portion that you want to show and include in the Word document, and then convert all the Word document to a PDF file. Somebody is still confused. So what is the confusion? What's the question? Okay, I'm just waiting to see your message. You can speak out or type your message quickly. So you take screenshot only for the extreme list size values for case 1 and 3. And for case 2, where you get a bad alloc error message for some list size value. So why I did not specify a list size value for case 2? Because it depends on your computer. And some people sent me emails that they did not get a bad alloc error message at all. That's okay too, because as I said, it depends on your computer, means it depends on the RAM, memory, everything available in the computer. So if your computer has a lower RAM, like 4 GB or 2 GB, you may get a bad alloc error message for list size values of 300 or 3000, 5000 and so on. But if you really have, say, 16 GB or a 32 GB RAM, that means your computer has sufficient memory to handle case 2. And if you see what case 2 is, you are not deleting the previously allocated memories for your array. So that means you're using up a lot of memory space. So if you still have sufficient RAM, you may not get the bad alloc error message. And for those people, I would have replied back to try beyond 10,000. So try to create list size of 20,000, 30,000, 40,000 and so on. So I am hopeful that you will get an error message as you increase list size to these numbers. So I asked them probably to go up to like 100,000, I guess. And if you still did not get error message, I asked you to just, in that case, probably I want you to take screenshots for every 10,000 increment you are doing and include those screenshots. But if you really have 8 GB or 4 GB or something like that as a RAM, I expect you to get an error message within 10,000 as a list size. Okay. So if you do not get a 10,000, try 20,000, 30,000, and as you increment by 10,000, you will get the error message. Okay. So Ariel, maybe your question has to do something with the environment, right? So You get error message every time I try to add the algorithm class. So that means you are not probably linking up all the code. So that has nothing to do probably with the assignment, what you're supposed to do for the assignment. So you have to load the code properly in your environment that you are working on. Okay, and you should have done this in 118 and 119, how to write a code in that environment that you're working on. So do we do increment by 1 or 1000? You increment by 1000. So it's like 1000, 2000, 3000. You increment by 1000, not by 1. So if, as I said, if the error message did not come for 10,000, just try for 10,000 to 20,000. So after 10,000, increment by 10,000. Until 10,000, increment by 1,000. After 10,000, increment by 10,000, 20,000, and so on. You should not get error message for case 3. That's the fix or change to the code you have to do. So if you look at the what you call the requirement for case 3, I say enhance the given code. So if you use the same code as case 2 for case 3, you will get an error message. So you have to fix the problem that you have in case 2, and that's case 3 after the problem is fixed. So you have to go back and fix the code. It's a small fix that you have to add code to fix the problem. And in case 3, you should not get any error message. So again, people are confusing between two cases. So case 2 has a problem of not clearing up the arrays that were created as you double the size. So that means if you're not getting error message in case 2, that doesn't mean that everything is fine with your code. It has this problem of memory leak. That means the memory is unnecessarily wasted. So you'll not get an error message for very large list-wise values only if you have a very large RAM in your computer, as I said, 32 GB and so on. But that problem needs to be fixed in the code. So that's what you're doing in case 3. You're adding just one small line statement there in somewhere in your code to fix that problem of not clearing up the previously allocated memory spaces. So that's what you're doing in case 3 to clear up all those stuff to fix that memory allocated. If the algorithm class should be part of all this programming environment. So if you don't need to include it for assignment 1, there is don't need to you have to include it actually because of this function. I'll be using the min function. So you have to really include it, but let me see. One second. That the environment should have that. I think you're not including the header file in the right way. But let me. Okay, so if you have a problem in including the algorithm header file, which Notepad++ MinGW don't need the inclusion because they automatically include the algorithm header file. So do this change to your code. Where is this code? So just remove the min function and just say max size. So in the resize function, instead of saying having it as minimum of s and max size, just say index less than max size. And you should be able to do this right away because that's where the min function is used. And we have a min function there to make it more general to handle both increasing as well as shrinking the array list size. And the min function is part of the algorithm header file. So if you cannot run that or include it in your environment, remove the min function and just say index less than max size. That's a simple fix. But if you want to include the min function and the algorithm header file is not loading up, you can write another separate main function. This is just taking the minimum of two values in x and y and return the minimum of the two, like by just telling if x less than y, or you can say less than equal to y, return x, else return y. So If you do that, you don't need to really remove the main function. You can still hide as minimum of s and max size. So either way you can do it. If you cannot include the algorithm header file, I suggest you to actually do this, because this way you're still using the code I gave you and you're adding some additional code to work around that problem. Or just remove the min function and just have it as max size. So either way should be fine. Is that clear? No, I did not say increase max size. So you see what I did? I just said index less than max size. That's an easy fix. So you can do that. Okay. So I think you meant resize. Yes. So remove the main function and just have the resize function. Just run it like this: index less than max size. Why can't you see my screen? So let me. So this is the code that you will have. So use this code for the resize function. Right? So we are out of time, so you can still ask the time during office hours, which I'll start right after the class, around in another 5 minutes. And the TA is also going to be available, and I hope Landry has taken the attendance by now. So some people may have class at 1:30, so we'll stop the session right now, and if you have any questions you can email me or ask me during my the office hours. Okay. All right, so we'll meet on Thursday.